Welcome to the USB TypeC class. My name is Ravi Shah, and I'm a product applications engineer at NXP here in San Jose. And I'm part of the regional marketing team supporting secure interface and power products at NXP. Let me at least talk about what is USB Type-C. I think that is pretty intuitive. So we are all familiar with the different USB connectors we use on a lot of different consumer devices. Most probably we see Type A connector on the notebooks, on the big high-end tablets. We see the micro B connector on a lot of our portable devices like phones through which we charge. And you might have seen the big clunky Type B connector on the back of the printers. So one thing with USB is that there are a lot of different types of connectors as the USB technology evolved. And so now going forward, USB-IF introduced the USB Type-C connector, which is kind of the connector of the future. And there are a few things that it started to address. One thing is consumer friendliness in terms of flippability. So one of the biggest problems with USB so far has been we always plug it the wrong side in a couple of times before we get it right? Every one of us has done that. So what USB Type-C does is it is a flippable connector. So it is independent of cable orientation and plug direction. So you can really plug in either way. So it is a very small connector. It is compact. And as you can see here on the screen, it is smaller than your Type A, and it is very close to the size of micro B connector. Right? It is also independent of cable direction and cable orientation, as I mentioned. It can support USB 3.1 Gen 2 speeds, which is 10 gigabit per second. Most of our designs today are USB 3.1 Gen 1, which is 5 gig. But in future, everything is going to get upgraded towards USB 3.1 Gen 2. And at the same time, it is fully backward compatible, and it supports USB 2.0 signaling as well. And on top of the USB connectivity, it also added the flexibility to provide scalable power charging and to send video data through the same connector. So you truly have now one connector which can do fast data transfer in terms of USB up to 10 gig. You can do scalable power charging up to 100 watts. You can send video data in terms of DisplayPort and also support legacy USB 2 devices through the same connector. So it is truly, you can envision it as a last connector because it is a one connector which can do everything, data, video, and power, all through the same cable and through the same connector. So when you look at the TypeC standard, there are a couple of things I want to highlight. There are different standards written in parallel that kind of go along with each other. So to give you a quick example, when you plug something into your USB 3 port, you expect 5 volt, 900 milliamps out of it. That's the spec, right? Similarly, in the previous generation, USB 2.0, you can expect 5 volt, 500 milliamps out of it. Now, that voltage and current is fixed, right? You cannot change that. You cannot negotiate that. Similarly, in the Type-C standard, you can go up to 3 amps, so 5 volt 3 amps or 5 volt 1.5 amps if you just support the Type-C standard. So that means you have the ability to still do up to 15 watts with let's just say, a bare bone Type-C standard. But all of us have heard that, USB Type-C can do up to 100 watts, right? So where does this 100 watt come from? So you can support up to 100 watts if you support something called USB power delivery as well through your Type-C connector. And what it does is it adds the ability for you to do scalable power charging through up to 20 volt and 5 amps. That's how you reach 100 watts, right? And now if your system wants to support video data through the Type-C connector, you need to support something called alternate mode standard. So alternate mode, as you can imagine, the name says you are in a mode, you can think of it as a mode other than USB or along with USB. So it's an alternate mode, right? So when you combine all these three standards, you can do high-speed data, you can do 100 watts power, and you can do DisplayPort video through it as well. And at the same time, it also means that not all systems need to be that complex. You can easily envision a system that wants to adopt a Type-C connector, which is a next-gen connector, but you may not care about data. You may not care about 100 watt power. 15 watt power is good enough for you. then you can just support the TypeC standard. You'll still get 15 watt out of it, and you can still support 5 gig USB or going forward 10 gig USB through it. One thing to mention, alternate mode is very closely tied with the power delivery spec. So if you do want to support video over TypeC, you need to support the whole power delivery spec from a design standpoint, because that's how the messaging is written in the spec. So they both go hand in hand. I already touched upon power delivery. So power delivery, again, will give you the ability to do scalable power charging up to 100 watts. And you can also do role swapping, which means your power provider can become a power consumer, and a power consumer can become a provider. So to put it in a practical view, we are all familiar with charging our smartphones if we plug into our notebook. But using this, hypothetically, if your smartphone supports power delivery, and if your notebook supports power delivery, and if your operating system allows it, you can theoretically put juice back into your notebook from your phone if your phone is fully charged and your notebook is dying. So it just shows the tremendous possibilities of applications that can be supported with USB Type-C. Again, alternate mode. So alternate mode is needed because there is always a need to send video data through that one connector. And if you just send DisplayPort data through that, then you can enable syncs like HDMI, VGA through using some sort of dongle applications as well. So just supporting alternate mode truly makes it all-in-one connector through the way of alternate mode support. Real quick look at the pinout. You can see it is much more kind of complex than your typical USB 2 or USB 3 pinouts. And it also shows you how there is a pin assigned to do everything that I just mentioned. So right in the middle, you see your D plus D minus lanes. That is for your traditional USB 2 support. On either side, you see 2 pairs of high-speed differential signals on each side. That are your high-speed lanes for sending USB 3 data, your high-speed differential signaling. You have the appropriate VBus and ground pins for power and ground. And then you see some sideband signal pins called SBU1, SBU2, which are, as SBU stands for sideband signaling. And also 2 pins called CC1 and CC2. And CC stands for configuration channel. So those are essentially the pins used for communicating any configuration messages between 2 sides when they are connected over Type-C. So you can see how there is a provision to send all kinds of signal through this pinout. Now remember, the very first thing I mentioned is that it is very consumer friendly in terms that it is flippable, it is irrespective of cable or plug orientation. So if you look at the bottom view, which is a plug view, when you look at a plug, I'm just going to flip it for you to see what happens. So when I flip it, you will notice the biggest thing that happens is the high-speed lanes, the 2 high-speed differential lanes on each side, they just got swapped completely, right? And this is an important observation because as a designer, you will need to account for that flippability. So think of a notebook. Let's think of a notebook with a Type-C connector, and it supports USB 3. Now, I may plug in this way, or I may flip it. So my USB 3 lanes are going to get swapped. But internal to the notebook, I still need to understand how I'm going to route my USB 3 lanes into the chipset, right? So you can envision that essentially we will need some sort of data switches in the path to enable this flippability, okay? Quick look again at the power side, and this just shows you the priority order for power and how the USB spec has evolved. It gives you a nice picture. So starting from USB 2.0, which was at 5 volt, 500 milliamps, we are going down to Type-C. Without power delivery, you can get 15 watts through 5 volt, 3 amps. And if you do support power delivery, then you can jump up to 20 volts and up to 5 amps, right? So you can support up to, again, 100 watts. Real quick look at the CC channel. So one obvious question that will come to the mind is, if both sides could be power provider and receiver in general, and if both sides are Type-C, how do you determine who is going to be the provider and who is going to be the consumer from a power standpoint, right? And again, just to be clear, I'm not talking about OTG or from a data standpoint, who is the master and slave. I'm strictly talking about power standpoint. So there is a provision through the configuration channel, and On the left, you see I have written the word DFP. DFP is called a downstream facing port, which means the port that is going to become the power provider. And the mechanism, the way the spec works is the side that is going to become a downstream facing port will have a pull-up on its CC lines, and the side that is going to become a consumer device, a power consumer, will have pull-down resistors on its CC lines. And the values of these pull-ups and pull-downs are given in the spec. But that's essentially how, and this is called CC Logic negotiation, that when two sides plug in, they establish which side is going to have an RP, which side is going to have an RD, and that is what is going to drive which side is going to become the power provider and which side is going to become the power consumer. And also, when you support power delivery and alternate modes, the same channel is used for sending modulated messages on each side because it is a scalable power charging. So again, to put it in a picture, the way scalable power charging would work is, imagine my notebook having a USB TypeC supporting power delivery, and I have a tablet, for example, that also supports power delivery over Type-C. When they both plug in into each other, say notebook becomes RP, it decides that I'm going to be the power provider. The tablet says I'm going to be the power receiver, but now it's scalable. That means by default, say notebook will put out 5 volt, say 5 volt 2 amps. I'm just making up a number. So it's 10 watts. But tablet will send out a message trying to like snoop and see, is the other side PD capable or not? And of course, it will respond that yes, I am PD capable. So then the tablet can ask for a higher profile. The tablet can send again a message saying, I'm getting 5 volt 2 amps. Can you raise it up to 12 volt 3 amps? I'm just making it up. Let's say it's a high-end tablet wanting 35 watts. It will say, can you give me 12 volt 3 amps so it can really charge quickly and efficiently. And if the notebook is in a condition to send out that kind of power, it will say, yes, I'll give you 12 volt 3 amps. It will push the VBus rail up to 12 volt 3 amps, right? I'm just trying to give you a simplistic picture of what do you mean by scalable power charging. And to exchange these messages, you need to be able to send and receive PD-capable, PD-compliant messaging, which is described in the specification. The USB spec has all the details about what the messaging should look like so that both sides are talking the same language. So that was a very brief overview of the TypeC standard. Let's look at a real quick view of the adoption and the market. So Type-C has very quickly evolved in starting with our consumer devices really as the first thing. And we are quickly seeing the adoption of this connector and standard in things like tablets, notebooks, even phones. And one other thing I want to point out is the AC-DC application. When everything goes to Type-C, your power bricks are also going to become Type-C. Like how for our mobile devices, we have a USB adapter right now. And we just plug in any USB charger we see. If our phone charges through USB, we just plug it in. We really don't see if anything else matches, right? It's USB charging. So it's very generic. Similarly, you can envision all the AC-DC, high wattage AC-DC adapters also moving towards Type-C so that they can charge anything which is Type-C. Next wave of applications is really the peripherals, the consumer type of devices. So, we are already seeing hard drives, gaming controllers, can even foresee it going into projectors. Anything that connects to our traditional consumer devices are a good candidate for Type-C adoption, and they are all moving towards Type-C to take advantage of the higher power scale, as well as to be compatible with the next-gen USB standard that is quickly being adopted in everything. So a very quick look at what are some of the devices available in the market today. So these are the most popular devices available. So I've been able to put up pictures here. The new MacBook, which got released earlier this year, has a Type-C port. And in fact, it only has one Type-C port on it. So that means that is the only connector on the entire device. So it charges through that. It sends out USB data through that. It sends out video through that. So real application of an all-in-one connector. And then, the Chromebook Pixel, the Google Pixel, also has USB Type-C ports on it. And very recently released Nexus mobile device also has a Type-C connector on it. Right? So it is very popularly being adopted across the board. let me give you a very quick picture of what would it take from a design standpoint to implement a USB Type-C connector. So let's say you are designing a system that wants to have USB Type-C, and you want to support everything. Let's start with a superset example. So you want to support high-speed USB, you want to support USB 2.0, you want to support 100 watts power, and you want to support video as well, right? Everything. So on the right, I'm showing you the Type-C pinout. So what I'm showing is I'm envision it as a physical connector, and I've mentioned all the key pins there. The V-bus pin, the USB 2 lanes, USB 3 lanes. CC Logic is the CC pin where you're going to exchange the configuration information. And VCON is called a connector voltage pin. It is also one of the CC pins where there is always a steady 5 volts according to the spec. And then you have your sideband signals, SBU pin. And on the left is your system chipset. Now that could be your host controller, it could be an FPGA, it could be an off-the-shelf processor, it could be anything that is going to source all these different types of data that you want to support. Okay? So the very first thing you need between the connector and your chipset is something called a PDFI, or a physical layer PD device. And why do you need that? Because as we established, if you are going to support PD, if the other side is going to support PD, they both need to talk the same language. So they both need to be able to exchange messaging that they both understand, which is compliant to the PD spec, and it is a BMC encoded messaging as per the spec. So this is what the physical layer device essentially does. It takes the message that wants to be sent out, it'll put it in the right packet structure and send it out, and it'll read the message that is coming in and tell its own system that, hey, this is what I got from the other side. So obviously, along with the PDFI, you can envision that you will need a MCU. Why MCU? Because MCU is your PD controller. It is your power delivery controller. It is your system policy manager, where you will have a fully compliant state machine running, essentially, that is going to govern everything. So microcontroller is the one which is going to tell your PDFI what to send out and interpret what the PDFI received, right? So they both go hand in hand, and they both can talk over I2C or SPI interface. But MCU is really the heart of the system where you put in your PD controller firmware and your policy engine. And that is where you'll write your application layer code to distinguish yourself from somebody else, and also to kind of make sure what profiles you want to support, right? Not everybody can support 20 volt 5 amps. So where do you write all that what are the specific things about your system? That is what goes into that PD firmware onto the MCU. From a power standpoint, then you can envision the use of a load switch, because again, load switch is going to provide a secure voltage in and out. Now, because everything could be running at different profiles, so say I'm a slave device. Let's assume I'm a slave device, and I only want 5 volt 3 amps. And if I plug it into something that is power delivery capable, what if by mistake it puts out 20 volts, for example? So if I have a load switch at my input, I can regulate. I'll only switch in the right amount of voltage and current. So it is essentially an over voltage protection, over current protection, reverse current protection type of device for your own security. And same use case if you're a power provider, to be spec compliant, you want to regulate, or you want to make sure that you are putting out the right amount of voltage and current. So it is a use case for both directions, right? So appropriate load switches will be needed for depending on the use cases. Then data switches. So we established that we'll need data switches for the high-speed path to support the flippability of the plug, right? So depending on the use case, again, whether you are only supporting USB 3 or whether you are supporting USB 3 and video both at the same time, you may need a different type of switch, but essentially you will need anywhere from a 2-to-1 switch, which is a simple USB 3 switch, to a cross-point switch, right? Because you want to support flippability. And then finally, you'll need some signal conditioner on the path. So again, depending on your signal integrity budget, the losses through the entire system, you'll need some sort of redriver in the path. And of course, some filtering and ESD protection for your port itself, for the connector, physical connector that we all are very familiar with. And finally, I'll touch towards the end. Authentication is another piece of it. And authentication really means security, making your entire connection secure. And the best way to visualize this is if I'm an accessory or if I'm a device, what if I can authenticate what is plugged in on the other side? And I will only negotiate power, I will only send out data if I can validate that the other side is a genuine accessory or if it's something that I support. Because it is only going to make my device safer. We have already seen instances around USB Type-C because of the higher power where if you plug in an accessory and that's not designed right, it can blow up your own host system. Or if your host system is not right, it can blow up your genuine accessory. So there are a lot of use cases that can go around authentication. And NXP is one of the leaders when it comes to security and authentication solution. That's why we are showing a block in an authentication solution that can be potentially added to make any of your Type-C system secure. And all the blocks that you see in white is what NXP offers. So NXP has a full system solution to enable any kind of USB Type-C design and solution. And you can see how many different blocks are required to build a full capable USB Type-C solution. Now real quick, let's try to simplify this. What if you can say, what if I want to have a system that I'm happy with 15 watts, I don't need to send or receive 100 watts, and I'm okay with USB 3.1, I don't even care about video. What if I want to build that kind of system? So you can see the system will simplify. So instead of a PDFI and MCU combination, I'll use something called a CC Logic device, because what that will do is just do your CC Logic negotiation. It will just say whether you're going to be a downstream facing port or an upstream facing port, and it will detect what kind of current and voltage is coming in. So it's a much simplified device compared to a PDFI and an MCU. You won't need any firmware because there is essentially no policy to manage, right? It pretty much becomes like your traditional USB connector where if you plug in and if your design is for 15 watts, that is what they are going to get, right? There is no scalable request here. And since you're only going to support USB 3, you are not going to do any display port or alternate mode. All you need is a 2-to-1 switch. So because your USB 3 data could be coming from one side or the other depending on how your plug is plugging in, right? And then again, optionally, some signal conditioner and some ESD protection, right? So you can already see we have simplified the system a little bit. And now if I go to the simplest use case, where you can say, I want to adopt a Type-C connector, I don't even care about USB 3.1 data, right? I'm happy with legacy USB 2 data, and 15 watts is obviously more than enough for me. Then you don't even need any data switches in the path. And can any one of you tell me why no data switches in the path? Because remember the pinout, the D plus D minus lanes were right in the middle. So even when you swap the plug, your lanes are not going to get swapped. So USB 2 could be connected straight through into your chipset. So it is the simplest implementation you can get with USB Type-C, right? So I do want to touch very quickly upon the PDFI and the CC Logic solution. So what the PDFI device does on the right, PTN 5100, it has all the baseband communication blocks and all the IP necessary to talk the PD language. So that's kind of all the blocks in the blue. And it also integrates the high power blocks needed, which I have shown on the top, like your VCON switch, some high power FETs, and basically design necessary to directly interface with VBus, which can go up to more than 20 volts to be over voltage protecting, right? So it is really an integrated physical layer device solution to support PDFI, to support power delivery and alternate mode applications. And at the same time, as I mentioned, if you do not want to support power delivery, you're happy with 15-watt design, you don't want to support alternate mode, then on the left is just a simple CC Logic device. All it does is negotiates CC Logic, the RPRD, and I'll show you more details on that. But this is a real quick overview of the PDFI IC. So I've listed the functions here. You can take a look when you refer to the slides later on. NXP also has fully compliant PD firmware, the fully firmware as per the PD spec that Steven is going to touch upon a little bit. And then the 50 and 50 device, which basically does the CC Logic detection. It can detect VCON power. It can detect what kind of accessories are plugged in. So kind of a simpler use case if you do not want to support power delivery, right? So if you want any more information on the PDFI and CC Logic, or in general on anything that I touched upon, feel free to contact me. I'll be available outside after this presentation, and we can talk. So again, to reiterate, this is a system solution using 50 on 50. So if you just support 15-watt system, you can use a USB 3 switch, a CC Logic device, and potentially a load switch. And this is a real quick snapshot of different switches that are available at NXP. So on the top left is a simple 2-to-1 switch. So if your application is only for USB 3.1, then all you need is a 2-to-1 switch. Now you may want to add a redriver to it. So the device below it is an active switch. So it's a redriver plus 2-to-1 switch. And then the device in the middle and onto the right are more complex. They are crossbar switches. And let me just give you one example of why you would need those. So say if you're doing USB 3.1 and video at the same time. Now you would question, how can I do both at the same time? Again, if you remember the Pinout, we had 2 sets of differential channels on each side. So through one, you will send your USB 3 TX-RX. Through other, you can send, say, 2 lanes of DisplayPort, which can still do quite a bit of resolution. And now when you flip the plug, your DP lanes are going to get swapped, and your USB lanes are going to get swapped too, right? So essentially, you need a crossbar switch. So that's what those switches are, depending on your application. How many lane crossbar switch do you need? Do you need a 4-lane crossbar or a 6-lane crossbar? Okay. And then for the sideband signals, when you send out DisplayPort, you'll need to switch your aux signals appropriately as well. So we have a big portfolio of very generic analog switches that can be used to switch any sideband signals going through the TypeC as well. And finally, a real quick look at the USB 3 redriver portfolio. So again, we have what we call a half port or a single channel, which means if you just want to optimize your TX or RX path, you can do that. Or if you just want to optimize your full port, which means TX and RX both, then we have a solution for that. Or if you want to optimize 2 ports, we have a dual port solution, which means 2 lanes of TX and RX. You can redrive 2 physical USB 3 ports. So with that, I'm going to turn it over to Steven, and where he'll go in more detail about microcontrollers.
USB TypeC is vastly different from previous generations of USB, not just from a connector standpoint, but also from a protocol standpoint. So like Ravi mentioned, you can run not only just the typical CC communication, but also you can run power delivery. You can run alternate modes like DisplayPort. And on top of that, you can also run vendor-defined messaging. So what this does is you can have 2 Type-C ports talk to each other and interact rather than just have data flow through each other. And this is actually how NXP achieves the authentication. So with all these protocols that can be going on between Type-C devices, you can imagine that there's strict timing requirements. And so really the MCU is needed in order to adhere to the spec and to make sure that between different vendors, products can still be interoperable. So you can think of the microcontroller as kind of like a PD policy manager, as he mentioned. So NXP has a broad portfolio of small, power-efficient microcontrollers. And you can think of a microcontroller as also as a resource that you could leverage to not only achieve the base Type-C functionality, but also to add on extra functionality that may or may not be required, kind of like authentication. And NXP also has in-house USB PD firmware that's fully compliant, and it's very configurable in order to achieve a use case for a system and an accessory. So just to quickly go over that, in general, Type-C can be split into 2 use cases: system, which is kind of like what you would think of when you hear the word host. So it's generally just like a motherboard for a laptop or desktop. And if you're using an NXP solution, the hardware configuration would be the PDFI, the PTN5100, and a microcontroller like an LPC 1115. For an accessory, which is a Type-C device that typically plugs into the host, and you'll see here it says USB based in parentheses. That's because most accessories nowadays, they implement DisplayPort alternate mode, and a requirement for that is to actually have the device enumerate itself as a USB 2.0 device for error handling and whatnot. So for this, the configuration would be a little bit different. You swap out the 1115 and put in an LPC 11U35, which is kind of like a USB version. And so if you're not running DisplayPort alternate mode, you don't necessarily need to change the microcontroller because then you wouldn't need the USB functionality. But NXP adds value. So if there is a USB on the accessory, then I'll talk about this later, but you can do in-field updates. So on the right, you'll see the PD firmware features. And as I said, the firmware is highly configurable. So really, each of these bullet points can be enabled or disabled in the firmware. So you can quickly turn a hardware from a system to an accessory or vice versa. And on the third row, you'll see power adapters. This is a little bit different because there's analog to digital conversion in the hardware. But you can think of this functionally kind of like a subset of a system, since it's essentially a DFP source that runs USB power delivery. Like you mentioned, in System Standalone, there's USB PDFI. You have a microcontroller to manage the PD policy. You have the load switches for USB PD and safety features like over voltage lockout and over current protection. You need the high performance switches for the super speed lanes. And you may or may not need signal conditioners. And you have ESD, TVS protection diodes for voltage clamping and whatnot. And you can optionally have authentication. So what I want to highlight here is that in a system standalone, there's typically an embedded controller, like in a motherboard. And we assume that it's in the system chipset block right here, and it's connected to the microcontroller through I2C. So really what happens is that as the MCU is the PD policy manager, you can configure it to be autonomous, where it makes all the PD decisions itself, or you can put it into non-autonomous mode, where the MCU will actually raise an interrupt to the EC, and the EC will actually read what's going on through I2C and actually make the decision. So just to give you a little background on the LPC 1115, it's, as far as TypeC is concerned, it's a power efficient Cortex M0 up to 50 megahertz, 64K flash, 8K RAM. There's a 10-bit ADC. This can be used or not used. For instance, if you have a custom design requirement where you want to do something if VBus drops below a certain voltage threshold, you can use the ADC to detect that. There's 42 GPIOs, so there's plenty of GPIOs for controls of the load switches, data muxes, whatnot, and maybe even throw in another PTN to make a dual port design. And it comes in a small BGA package. So this is the general block diagram for the accessory solution. The biggest difference between the accessory and system is that there's no embedded controller. So really the MC is the only thing making decisions here. And what I want to highlight is that, like I said, you would use a USB-based part most likely to implement not just Billboard for the DisplayPort alt mode requirement, but also for DFU for firmware updates. And I'll talk about that more in detail later. So just more specs about 11U35. It's pretty much like the cousin of 1115. So still a Cortex M0, a little bit more RAM, 12K instead of 8K. But really what's important is that it supports USB 2.0 full speed. So here's this firmware architecture of the NXP's USB PD kernel. Like I said, it's very flexible, so it could be configured for a variety of applications, whether it's system or accessory. And then it's also expandable to be used in multi-port USB TypeC designs. And NXP has been working with Elysis very closely ever since they've been doing compliance tests for USB TypeC. So just to make sure that we are 100% compliant with their tester. So like I said, the biggest difference between an accessory and a system is the fact that there's no embedded controller in the accessory. So for a system situation, the EC can actually update the MCU through I2C. For a accessory, like a protocol connector converter like TypeC to VGA, it's a closed system. And if you have no USB, then the MCU just can't talk to the outside world. So if you have USB, not only do you fulfill the DP alt mode requirement, you could also do firmware updates in the field. So in the internal ROM of the MCU, there's something called USB in systems programming mode, where if you set a certain pin low, another high, then you can actually enumerate the MCU as a mass storage class device to the host. and then you can delete the current firmware, drag in the new one, just like you're putting files on a flash drive. But this is not the most customer-facing solution. So NXP also provides a device firmware update secondary bootloader, or DFU SBL. And the main points of a DFU SBL is that it resides in user flash, and it provides added security. So if you want to encrypt your firmware before you program it, then the SBL can automatically decrypt it before it programs it to flash. And also, the firmware update will actually have a section for CRC checksum for code integrity. Make sure you're not programming a new firmware that's broken. And with this, in conjunction, you would use two host tools. The first is an image creator tool. This just takes in the new application binary, slaps on the SBL, and merges it together and outputs it as one binary. You can encrypt it with the 128-bit symmetric encryption algorithm. And like I said, it inserts and generates a CRC checksum. And the other tool is a DFU utility. This is what actually triggers the context switch between USB PD kernel and secondary bootloader. And this is also the tool that communicates to SBL to send in your firmware. So just to give you an example of how expandable the firmware is and our solution in general. So this is a very typical, generic, simple one-to-one adapter, Type C to VGA. This block diagram should look familiar now. But what if you wanted to take this existing design and actually make something much more complex, like a 1-to-3 multi-port adapter, like Apple's digital multimeter AV adapter. So here, not only are you doing Type C to VGA, but you're also doing Type C to VGA with USB 2.0 or 3.0, and Type C for charge through port. So here, you would expect much more changes, but as I said, the firmware is very configurable, so you could actually configure the firmware to expand it so it's multi-port. The MCU has enough GPIOs and horsepower to handle 2 ports. So really all you have to do is slap on another PDFI to handle the second Type C port. And so with that, I'll hand it back to Ravi.
So let me touch upon the load switches a little bit that I talked about early on. So as you know, load switches are basically integrated FETs with security features built in. Depending on the application, could be OVP, over current protection, reverse current protection, over temperature protection. But when it comes to Type C, there are 2 main use cases that I want to touch upon. So on the top, you see a charging path use case. So imagine a Type C connector on your left, and then inside on the right is your PMU and your OTG regulator. So on the top, what I'm showing is you could be charging up to 20 volt 5 amps going left to right, as I've shown. So you need a 20 volt operational switch, with over voltage protection and over current protection. And then on the bottom path, what I'm showing is an OTG use case where you may want to put out 5 volt 3 amps, but at the same time, it also has reverse current protection to block, during the charging case, right? So there are 2 clear use cases for load switches and your power path protection. One is the charging use case. The other one is, the outputting. So a DFP and a UFP use case. Right? Real quick on the AC-DC adapter. So now earlier on, I touched upon that AC-DC adapter is also a big application. As all the power supplies are also moving towards Type C, based connector. So now, if you think of, theoretically, how would you make a Type C power adapter? You can say, oh, I'll take my AC-DC front end and then put in the PDFI and the MCU, right, to do the negotiation and support different profiles. But that would be too complex, right? It will be too many chips. So what we have done is we have integrated a lot of these things. And NXP already has a big portfolio of, the primary, front end. So like synchronous rectifier and the primary controller. So as I was shown in this block diagram, this is our integrated solution for making an AC-DC PD-capable charger. So the 1936 and 1993 are the primary controller and the synchronous rectifier. And the TEA 1903 on the right bottom is the integrated PD controller with the secondary. So it's an integrated PD secondary side controller for your AC-DC application. So just something to keep in mind, that how you can have a very integrated and a compact solution for a PD capable charger as well. Finally, authentication. So again, we can have a whole separate speaking session on authentication itself, but I did wanted to throw it out there to get you thinking that there is a way to make a link absolutely secure around USB Type-C, and for that, the reasoning for that could be different for everybody. It could be simple protection, it could be brand and IP protection, it could be some licensing mechanism, it could be anything. But there is a way to include authentication in your design and get that security use case out of it. And finally, NXP is very big on standard products, as we call it, which is all your EST protection, filtering, diodes, MOSFETs. So we have a huge portfolio of solutions there to support anything that is needed around a USB Type-C solution as well. So lastly, I really want to summarize by this, that NXP offers a complete USB Type-C solution, no matter what kind of configuration you want to do. And the real practical benefit you will see out of this is that it is really a one-stop shop. So you not only have all the different MCUs that Steven mentioned, you have the flexibility to pair the PDFI with any kind of MCU that you want, depending on the resource requirements. You have the load switches. We also address the data paths through the high-performance data switches, EST protection, and even value-added things like authentication. So it's truly a one-stop shop, along with the PD firmware, that we already have. And I think the biggest impact going forward it can have is it can help you prepare for interop testing, because we have boards built working fine. So if you are trying to get something compliant, if you're trying to make a fully functional system, you can leverage all the experience we have because we designed the complete solution and we have it working. Finally, for your reference in the presentation, you will see I have included a complete product summary of every kind of device that is available from NXP around USB Type-C ecosystem, along with the microcontrollers as well. So you can refer to this for your reference. So that is the end of my presentation. I know it was very quick. Thank you all. Thank you for your time.